Introduction. This video teaches the fundamentals of gases to learners and viewers who desire to enrich their knowledge of the subject in physical chemistry. The study is detailed in real-life applications and engages viewers and learners in solved exercises, as well as problems to be solved, with guides to obtain the correct answer to each problem. Learners and viewers should develop the zeal to follow up with the teachings in this resource and gain in-depth knowledge and applications to fundamental concepts in the study of gases. Outline. 1.0 Gases and other states of matter. 1.1 Key characteristics of gases. 1.1.2 Practical considerations to the kinetic theory of gases. 1.2 Why are gases difficult to manage than liquids? 1.3 Common examples of gases. 2.0 Ideal gas equations and their derivatives. 2.1 Ideal gas equation, general form. 2.2 Assumptions of the ideal gas law. 2.3 Gas velocities. 2.3.1 The Maxwell-Boltzmann distribution for illustrating speeds or velocities of gases. 3.0 Relationship between the density and molar mass of gases. 3.1 Interpretation of the equations for the density of gases shows that. 4.0 Dalton's law of partial pressure. 4.1 Mathematical expression of Dalton's law. 5.0 Transport properties of gases. 5.1 Mean free path length. 5.2 Molecular diameters. 5.3 Collision frequency. 5.4 Coefficient of dynamic viscosity. 5.5 Thermal conductivity of gases. 5.6 The diffusion coefficient of gases. 6.0 Real gases. 6.1 Key characteristics of real gases. 6.2 Differences between real gases and ideal gases. 6.3 Real gas equations. 6.3.1 Van der Waals equation of state. 6.3.1 Practical explanation of Van der Waals equation of state. 6.3.2 Virial equation of state. 6.3.3 Soave-Redlich-Kwong, SRK, equation. 7.0 Application of the concept of real gases. 7.1 Production of liquefied natural gas, LNG. 7.2 Production of liquefied petroleum gas, LPG. 7.3 Production of compressed natural gas, CNG. 7.4 Separation of the component of air. 8.0 Joule-Thomson experiment. 1.0 Gases and other states of matter. The picture here shows the states of matter and their phases of transitions. Interestingly, the state of matter are solid, liquid, gas, and plasma. This shows 4 states of matter arranged in order of increasing difficulty to contain, due to the degree of disorderliness that makes up the component of matter in the substance. Sir William Crookes as far back as 1879 discovered plasma as the 4th state of matter. Plasma is a state of matter that results from a gaseous state having undergone some degree of ionization. It thus consists of a significant portion of charged particles, ions and/or electrons. While rarely encountered on Earth, It is estimated that 99.9% of all ordinary matter in the universe is plasma. Stars are almost pure balls of plasma, and plasma dominates the rarefied intracluster medium and intergalactic medium. Plasma can be artificially generated, for example, by heating a neutral gas or subjecting it to a strong electromagnetic field. Examples of plasma are lightning, stars, fire, etc. A gas is a state of matter in which the particles, atoms or molecules, are widely spaced with no fixed shape or volume, free to move in all directions, easily compressed and expandable, low in density compared to solids and liquids. 1.1 Key characteristics of gases. 1. No fixed shape or volume. Gases take the shape and volume of their container. 2. High kinetic energy. Gas particles move rapidly and randomly in all directions. 3. Compressibility. Gases can be compressed much more easily than solids or liquids due to the large space between particles. 4. Low intermolecular forces. The forces between gas particles are very weak, allowing them to move independently. 5. Diffuse and mix easily. Gases spread out and mix with other gases uniformly. 1.1.2 Practical considerations to the kinetic theory of gases. The kinetic molecular theory of gases explains the behavior of gases by considering the motion of individual gas molecules. It provides a framework for understanding how gas pressure, volume, and temperature are related based on the microscopic interactions and motion of gas particles. Here's a practical explanation of the main postulates of the kinetic molecular theory. 1. Gas particles are in constant, random motion. Gas molecules move constantly in all directions at varying speeds. This random motion is a fundamental characteristic of gases. Example: think of the air molecules in a balloon. They move around rapidly, colliding with each other and the walls of the balloon. The faster the molecules move, the higher the temperature of the gas. 2. Gas particles are separated by large distances relative to their size. The size of individual gas molecules is extremely small compared to the distance between them. This means that gas molecules are mostly empty space, which explains why gases are compressible. Example: imagine a balloon that is inflated with air. Even though the balloon may seem solid, the vast majority of the space inside is just air molecules moving rapidly, and the balloon can be squeezed or compressed because the molecules are far apart and can be pushed closer together. 3. Collisions between gas particles are perfectly elastic. When gas molecules collide with each other or the walls of their container, the collisions are elastic, meaning there is no loss of kinetic energy. The total energy before and after the collision remains the same. Example: in a basketball, the gas particles inside collide with each other and with the inner walls of the ball. These collisions don't lose energy, in an ideal case, but maintain the internal pressure of the ball, which helps keep its shape. 4. There are no attractive or repulsive forces between gas particles. Gas molecules do not exert any significant force on each other, either attracting or repelling each other, unless they collide. This assumption is idealized because real gases do have some intermolecular forces, but they are small compared to the energy of motion in the gas particles. Example: in the case of nitrogen gas, N2, in the atmosphere, each molecule behaves as if it is not interacting with the others, except when they collide. This lack of intermolecular attraction allows nitrogen gas to fill the entire atmosphere and expand freely. 5. The average kinetic energy of gas molecules is directly proportional to the temperature. The kinetic energy of gas molecules increases as the temperature increases. In fact, the average kinetic energy of the gas molecules is directly proportional to the absolute temperature, in Kelvin. Example: when you heat a can of air, the molecules inside gain more energy and move faster. If you increase the temperature of the gas in a container, the molecules will collide with the walls more frequently and forcefully, increasing the pressure, assuming the volume is constant. Viewers and learners should deduce how these kinetic theories of gases will be explained by the gas laws as we proceed in this video. 1.2 Why are gases difficult to manage than liquids? This is better explained by the properties of gases as shown below. 1. Lack of definite shape and volume. Gases expand to fill any container, meaning they don't have a fixed shape or size. Unlike solids and liquids, you can't hold a gas without enclosing it in a sealed container. 2. Compressibility. Gases can be easily compressed, which makes their volume and pressure very sensitive to changes. This makes it harder to maintain consistent conditions, especially in systems like gas pipelines, cylinders, or engines. 3. High diffusibility and leakage. Gas molecules move freely and spread out quickly, which means they leak easily through tiny holes or porous materials. Even small leaks can be dangerous, especially with toxic, flammable, or pressurized gases. 4. Invisible and odorless nature, in many cases. Many gases are colorless and odorless, making them hard to detect without specialized equipment. This increases the risk of undetected leaks, explosions, or exposure, e.g., carbon monoxide. 5. Storage challenges. Gases often require special storage conditions, such as high-pressure tanks, e.g., oxygen cylinders, or very low temperatures, e.g., liquefied natural gas. These containers must be strong, airtight, and temperature-resistant, which increases cost and complexity. 6. Sensitive to temperature and pressure. Gases expand or contract significantly with changes in temperature or pressure, according to gas laws like Boyle's and Charles's laws. This requires careful monitoring to avoid dangerous buildups of pressure or equipment failure. 7. Complex behavior in mixtures. When gases are mixed, like in the air or industrial processes, their behavior can be hard to predict due to interactions, partial pressures, or reactions. 1.3 Common examples of gases. Oxygen, O2, essential for respiration. Carbon dioxide, CO2, produced by breathing and combustion. Nitrogen, N2, makes up about 78% of Earth's atmosphere. Hydrogen, H2, the lightest gas, used in fuel cells. Helium, He, used in balloons and cryogenics. A natural gas, mixture of hydrocarbons from C1, C2, C3, C4 to C5 plus. Solved exercise 1.0. What is the major difference between gases and plasmas as states of matter? Answer: plasmas are a highly energetic, ionized state of matter, while gases are made up of neutral particles. Problem 1.0. Classify the two substances neon signs and water molecules at 100 degrees Celsius into two different states of matter. 2.0. Ideal gas equations and their derivatives. The ideal gas equations explained from Boyle's and Charles's laws are as follows. Equation 1 shows the equation of Boyle's law. This states that the volume, V, of a fixed mass of gas is inversely proportional to its pressure, P, at constant pressure, that is V equals K/P, where K is the V and P constant, as shown in equation 1. Equation 2 shows the equation of Charles's law. The volume, V, of a fixed mass of gas is proportional to its temperature, T, at constant pressure, that is V equals kT, where K is the V and T constant, as shown in equation 2. 2.1. Ideal gas equation, general form. Combining both Boyle's and Charles' equations by making K the subject of the formula, we have that K equals PV and K equals V/T. Therefore, P1V1/T1 equals P2V2/T2 is the general or combined gas equation, as shown in equation 3. Note that this equation can be used for solving problems related to both Boyle's law and Charles's law, provided the constant terms are used as required. Also, the combined gas equation leads to the ideal gas equation, PV equals nRT, as shown in equation 4. Here, the term P2V2/T2 in equation 3 is equal to nR, where 1 and 2 represent two different instances in the container of a mixture of gas that varied at different physical parameters as described here. Note that, during calculations, one should be conscious of using SI units, then convert to any desired unit. Example, where pressure is in atm or Pa, V equals volume in liters or cubic meter, N equals number of moles of gas, R equals ideal gas constant with values in 0.0821 L atm/ mol K, 8.314 J/ mol K, or 8.314 m superscript 3 Pa/ mol K, and T equals temperature, in Kelvin. The choices of all other physical parameters to be used here depend on the unit of R. Solved exercise 2.0. What is the volume of 2 moles of an ideal gas at 1 atm and 273 K? Answer: given N equals 2 mol, P equals 1 atm, T equals 273 K, R equals 0.0821 L atm/ mol K. Using the ideal gas equation, equation 4, volume equals no of moles multiplied by gas constant and multiplied by temperature divided by pressure. Therefore the volume of the ideal gas is equal to 2 times 0.0821 times 273/1 equals 44.8 L. Problem 2.0. If the room that you are sitting in right now is 16 feet long by 12 feet wide by 10 feet tall and at 22 degrees Celsius, then the number of moles and mass of air present in the room are moles and kg respectively. Take the molecular weight of air to be 29 grams per mole. Answer: 2246 moles and 65.2 kilograms. To obtain the answers to problem 2.0 above, the dimensions will be evaluated to obtain the volume of the room. Then the ideal gas equation will be used to calculate the number of moles present. Also, the mathematical equation showing the relationship between the number of moles of a substance, mass of the substance, and the molar mass substance will be used to calculate the mass of the substance. 2.2 Assumptions of the ideal gas law. The ideal gas law assumes gas molecules have no volume, point particles. No intermolecular forces between molecules. Collisions are perfectly elastic. Gas particles are in constant random motion. These assumptions work best under low pressure and high temperature conditions. Note this for the properties of ideal or perfect gases, which will form the major difference for real gases. 2.3 Gas velocities. The Maxwell-Boltzmann distribution function describes the fraction of molecules with a particular speed in a gas at a given temperature. This gives the probability distribution of speeds, or velocities, of molecules in a gas. From this distribution, we can derive expressions for the most probable speed, average speed, and root mean square speed. The Maxwell-Boltzmann distribution is as shown in equation 5, where f, v, is the fraction of molecules with velocity v. m is the mass of a gas molecule. Kb or K is the Boltzmann constant, 1.38 times 10⁻23 J/K. T is the absolute temperature, in Kelvin. V is the speed of a molecule. R is the universal gas constant, 8.314 joules per mole K. 2.3.1 The Maxwell-Boltzmann distribution curve was used to illustrate these speeds or velocities. Most probable speed, UMP, in equation 6, is the speed at which the largest number of molecules are moving. It corresponds to the peak of the Maxwell-Boltzmann distribution curve. The average speed, WAVG, in equation 7, is the mean of the molecular speeds in the gas. It is calculated as the average of all possible speeds weighted by their probability, and the root mean square speed, AMS, in equation 8, is the square root of the average of the squares of the molecular speeds. The relationship between the three forms of speeds or velocities are shown in equation 9a. The ratio of root mean square velocity to most probable velocity is 1.2247. Equation 9b. The ratio of all three velocities to the most probable velocity, beginning with root mean square velocity and ending with most probable velocity, is equal to 1.2247 is to 1.128 is to 1. Equation 9c shows the different forms of speed arranged in a decreasing order, AMS, WAVG, AUMP. Let us consider a closed system with one molecule of gas, having the force, F, which strikes the walls of the container or system at an area, A. It is obvious that this molecule will not remain at its position of impact, but move backward to its initial position. Equation 10a shows the expression for the force of the gas molecule, which is directly proportional to its mass and acceleration. The ratio of force to surface area at which the molecule strikes the surface of the container is shown in equation 10b. The impact of the molecule on the container, momentum, in the forward direction is shown in equation 10c, and the total impact of the gas molecule as it hits the surface and returns to its initial position, which makes the momentum double, as in equation 10d. Equation 11 shows that the force exerted by the gas molecule is proportional to its rate of change in pressure. Equation 12 shows the expression for the rate of change in momentum, mv, of the gas molecule in one direction, x, which is equal to the gas pressure, p. These are obtained from Newton's second law of motion. Considering that only one-third of the total molecular velocity contributes to the pressure of the gas molecule on one wall of the container, and where the length of the container, L, is introduced to represent distance for rate of collision, the total force, total, exerted by the molecule of gas is given as the product of molar density, N, and molar mass, m, and square of the average velocity of the gas, and all divided by 3 times the length, L. This assumption leads to equation 13 and 14. So, the pressure of the gas molecule is directly proportional to the square of its velocity and inversely proportional to the surface area through which the molecule passes. This is observed in practice. It is then easy to make kinetic energy from equation 14, as we substitute the expression for the number of moles, N, to make equation 15. The terms of mass and velocity square in equation 15 are collected together and multiplied by half. Then the left-hand side of the equation is also multiplied by half as well, to balance the mathematical expression, making pressure, P, the subject of formula, gives the relationship between the pressure and average kinetic energy as in equation 16. Solve problem 2.1. The root mean square speed at which the average oxygen molecule is moving in a room at 30 degrees Celsius is m/s. The solved problem 2.1 is handled simply by substituting the molar mass of oxygen and its temperature in the desired SI unit into equation 8. 3.0. Relationship between the density and molar mass of gases. The kinetic theory of gases provides a microscopic understanding of the behavior of gases by relating the motion of gas molecules to macroscopic quantities like pressure, volume, temperature, and density. Also, from equation 15, if we collect the ratio of mass of the gas, m, to the volume, v, occupied in the container, we obtain the expression for the gas pressure, P, in relationship to its density, ρ, and average velocity, WAV, as shown in equation 17a. Similarly, the relationship between the gas pressure and density could be obtained from the ideal gas equation, PV equals nRT, making N equals m/mm, gives PV equals m/mm multiplied by RT, then P equals m/v multiplied by 1/mm multiplied by RT. Since m/v equal to density, ρ, then the pressure of the gas molecule, P, is equal to the product of density and gas constant and temperature divided by its molar mass. This gives equation 17b as the relationship between density, ρ, and pressure, molar mass, as well as the temperature of the gas molecule. In the above equations, the symbols stand for P equals pressure of the gas, N equals number of gas molecules, V equals volume of the container, M equals mass of one molecule of the gas, M equals molar mass of the gas, WAV equals average velocity of gas molecules. 3.1 Interpretation of the equations for the density of gases shows that 1. Density is directly proportional to molar mass. Gases with larger molar masses have higher densities, assuming constant temperature and pressure. 2. Density is directly proportional to pressure. At higher pressures, the gas molecules are more tightly packed, increasing the density. 3. Density is inversely proportional to temperature. As temperature increases, the gas molecules move faster and spread out more, reducing the density. This equation is very useful in understanding how different conditions, pressure, temperature, affect the density of a gas, and it can be applied to both ideal and real gases under certain conditions. Learners and viewers should see Solved Exercise 3.0 for more application in this section. Problem 3.0. The ammonia molecule that was produced from the Haber process was compressed to a pressure of 107,080,000 millimeters of mercury at a temperature of 50 degrees Celsius. Prove that the compressed gas was made up of pure ammonia compound. R equals 8.314 J/mol K. Relative atomic mass of nitrogen and hydrogen are 14 g and 1 g, respectively. Density of pure ammonia compound at 50 degrees Celsius is 0.638 kilograms per cubic meter. To guide you on the steps to obtain the correct answer to the question in problem 3.0, calculate the density of ammonia at the given temperature. To have consistency in units, the unit of pressure should be converted to meter mercury, mHg, while that of temperature in Kelvin, K, as well as molar masses in kilogram, kg. If substituting these values into equation 17b gives 0.638 kilograms per cubic meter as the density, then the answer is correct, as the density of pure ammonia compound at 50 degrees Celsius is 0.638 kilograms per cubic meter as given in the question. Note that the density of substances, including gases, varies as their temperatures vary, same with pressure, while their molar masses remain the same. Learners and viewers should also endeavor to attempt problem 3.0 for more knowledge. 4.0 Dalton's Law of Partial Pressure. Dalton's law of partial pressures states that the total pressure exerted by a mixture of non-reacting gases is the sum of the partial pressures of the individual gases in the mixture. In other words, the pressure exerted by each gas in the mixture is independent of the pressures exerted by other gases, and the total pressure is the sum of these individual pressures. 4.1 Mathematical expression of Dalton's law. Equation 18 shows that the total pressure, total, of the individual gases in Figure 3 is equal to the sum of the pressure of gases in the container PO2, PN2, pH2, and PCO2 for oxygen, nitrogen, and carbon, 4, oxide respectively. Note that plus Pn shows that more gases can be added, provided they are not chemically combined. The partial pressure, pi, of a gas is the pressure that the gas would exert if it alone occupied the entire volume at the same temperature. The partial pressure, pi, of gas molecules can be expressed using the ideal gas equation, PV equals nRT. This is shown in equation 19, as I indicates pressure of the individual or pure gas and Ni indicates its number of moles. Also, the partial pressure, pi, of the gas molecule can be given in terms of its mole fraction, 11, and total pressure, pi, as shown in equation 20. Recall that the mole fraction 11 is the ratio of the number of mole, Ni, of a particular substance to the total number of moles, N total, of all substances present in the system, She equals Ni/total. Solve problem 4.0. The total pressure of nitrogen, oxygen, and chlorine gas is 5 atm. Consider the mole percent of nitrogen and chlorine as 65 mole percent. The partial pressure of oxygen gas is _____ torr. The solution of this problem is as shown. The mole fraction of oxygen will be determined, then the parameters substituted into equation 18, then the value in atm converted to its equivalent value in torr. Problem 4.0. Oxygen gas generated in the composition of potassium chlorate was collected with a volume of 128 milliliters at 24 OC and 762 millimeters of mercury. Calculate the mass in gram of oxygen gas obtained. Pressure of water vapor at 24 C equals 22.4 millimeters of mercury. R equals 0.00821 L.atm per Kelvin per mole. Consider these steps to obtain the correct answer to the question in problem 4.0. Partial pressure should be treated as the number of moles. There, you obtain the partial pressure of oxygen from that of water and the mixture, total pressure. Then, from the ideal gas equation, PV equals nRT, present N in the relationship of mass and molar mass and substitute into the expression to make the mass of oxygen gas the subject of the formula. Finally, evaluate to obtain 0.164 gram as the mass of oxygen gas in gram. 5.0. Transport properties of gases. The gas velocities discussed previously are also part of the transport properties of gases. Other transport properties of gases will be discussed here as well. 5.1. Mean free path length. The mean free path length lambda or lambda is a measure of the average distance a gas molecule travels between successive collisions with other molecules. It is an important concept in understanding the transport properties of gases, such as diffusion, viscosity, and thermal conductivity. Equations 21a and 21b show how the mean free path length is calculated using with and without the use of the Boltzmann's constant, Kb, respectively. Where lambda equals mean free path length, in meters. N equals number density of gas molecules, number of molecules per unit volume, N/V. Sigma or sigma equals effective collision cross-section area, in square meters. This depends on the size of the gas molecules and their interaction potential. Square roots of 2 here equals accounts for the relative motion of gas molecules during collisions, considering that the gas molecules are moving in random directions. If Kb equals Boltzmann constant, 1.38 times 10⁻23 J/K times 10 to the power of -23. T equals temperature, in Kelvin. D equals diameter of a gas molecule, in meters. P equals pressure of the gas, in pascals. 5.1.2 Derivation and interpretation from the equations of mean free path length of gases. The mean free path length lambda increases with temperature, T, because higher temperatures lead to faster moving molecules, which means they travel further between collisions. The mean free path length lambda decreases with increasing pressure, P, as higher pressures result in a higher number of molecules per unit volume, leading to more frequent collisions. The molecular diameter, d, is squared because it represents the effective cross-sectional area for collisions. Larger molecules have a shorter mean free path because they have a larger collision cross-section. Solve problem 5.0. Calculate the mean free path length of a gas molecule at a temperature of 300 K and a pressure of 1 atm. The diameter of the molecule is 2a. The solution to this problem shows that equation 21a is used and the physical parameters converted to SI units to be consistent with the unit of Boltzmann's constant. Pressure, P, is converted from atm to Pascal, and the diameter of the molecule, d, is converted angstrom, A, to meter, m. This gives us the mean free path as 2.30 times 10 m or 230 nanometers. 5.2 Molecular diameters. The equation 22a for the molecular diameter, d, of gases can be derived from equation 21b of mean free path, lambda, by substituting the mathematical expression for the effective collision cross-section area, sigma. Equation 22b could also be used for calculating molecular free path with just the combination of the square root of the fraction of the collision frequency and pi. Note that sigma equals pi d square. And all parameters in equation 22 remain as described earlier. 5.2.1 Derivation and interpretation from the molecular diameters of gases. Viscosity. The molecular diameter influences the viscosity of the gas. Viscosity is the resistance of a fluid to flow, and for gases, it increases with molecular size. The molecular diameter contributes to the frequency of molecular collisions, which affects the transfer of momentum between molecules. Diffusion. The molecular diameter also affects how gases diffuse. Larger molecules move slower and collide more often, which can reduce the rate of diffusion. Fick's law of diffusion is related to the mean free path and molecular size. Problem 5.0. The mean free path of a gas molecule is 200 nanometers at a pressure of 1.5 atm and a temperature of 300 K. Calculate the diameter of the molecule. A simple guide to this is that equation 22a will be used, and the answer is 3.2 times 10 superscript 1 m or 3.2 a or Armstrong. 5.3 Collision frequency. Collision frequency refers to the number of collisions a gas molecule undergoes per unit time. It is an important factor in determining the transport properties of gases such as viscosity, diffusion, and thermal conductivity. The more frequent the collisions, the more likely energy and momentum will be transferred between molecules, affecting these transport properties. Equation 23 shows the collision frequency of gases, which is directly proportional to the square of the molecular diameter, d, average velocity, WAVG, and number of density of molecules, n. 5.3.1 Derivation and interpretation from collision frequency of gases. The collision frequency is proportional to the square of the molecular diameter, meaning that larger molecules will collide more frequently. It is also proportional to the number density, n, meaning that more molecules in a given volume will lead to more collisions, and it is also proportional to the average velocity, meaning that faster-moving molecules will collide more often. Relation of collision frequency of gases to transport properties. Viscosity. The collision frequency affects how momentum is transferred between molecules, influencing the viscosity of the gas. Thermal conductivity. The rate at which energy is transferred between molecules through collisions also depends on collision frequency. Diffusion. The rate of diffusion depends on how often molecules collide and exchange momentum and energy. Solve problem 5.1. Calculate the collision frequency of oxygen molecules, O2, at a temperature of 300 K. The diameter of an oxygen molecule is 3.46 A. Take the number density, N, of O2 as 2.5 times 10 superscript 2 molecules / m superscript 3 at 1 atm and 300 K. Molecular mass of oxygen is 32 AMU. The solution to this problem is simple and has the major concerns treated in previous problems and teachings covered. So, the collision frequency of oxygen molecules here is approximately 4.98 times 10 collisions per second. This calculation demonstrates how to determine the collision frequency of gas molecules using the average kinetic energy and molecular properties. 5.4 Coefficient of dynamic viscosity. The coefficient of dynamic viscosity, eta, in equation 24 is a measure of a gas's resistance to flow. It describes how easily a gas can move or deform under a force. Viscosity is important in the study of fluid dynamics and affects transport properties like momentum transfer between gas layers and the rate of diffusion. In gases, dynamic viscosity depends on factors like temperature, molecular interactions, and molecular size. The physical parameters, as shown in equation 24, for the coefficient of dynamic viscosity are: eta equals dynamic viscosity in Pascal second or kilogram per meter per second. m equals molecular mass of a gas molecule in kg. kb equals Boltzmann constant 1.38 times 10⁻23 J/K times 10 to power (-23). T equals temperature in Kelvin. D equals molecular diameter in meters. P equals pressure in pascals. 5.4.1 Practical implications of the coefficient of dynamic viscosity of gases. Temperature dependence. Viscosity generally increases with temperature for gases. As temperature increases, molecules move faster and collide more frequently, leading to higher viscosity. Molecular size influence. Larger molecules, higher d, will result in higher viscosity because their larger size leads to more frequent collisions between molecules. Gas composition. Gases with heavier molecules or larger molecular diameters tend to have higher viscosities compared to lighter gases like helium or hydrogen. 5.5. Thermal conductivity of gases. Thermal conductivity, K, is a measure of a material's ability to conduct heat. For gases, it refers to how easily heat is transferred between molecules through collisions. Thermal conductivity plays a crucial role in understanding how heat flows in gases, such as in heat exchangers, atmospheric processes, and insulation. In gases, thermal conductivity depends on factors like temperature, pressure, and the molecular properties of the gas. Equation 25 shows the expression for the thermal conductivity of gases with the physical parameter described as follows. K uguale thermal conductivity, in watts per meter per Kelvin, WmK. CV equals specific heat at constant volume, in joules per mole per Kelvin, J/mol K. WAVG equals average molecular velocity, in meters per second. Lambda equals mean free path length, in meters. 5.5.1 Practical applications of the thermal conductivity of gases. 1. Heat transfer. Understanding thermal conductivity is critical in designing systems that need efficient heat exchange, such as radiators, air conditioning systems, and insulation materials. 2. Atmospheric studies. In meteorology, thermal conductivity helps explain how heat moves through the atmosphere and contributes to processes like convection and the greenhouse effect. 3. Industrial processes. Industries like cryogenics, aerospace, and energy production rely on the principles of thermal conductivity to manage and control heat flow in gases. Problem 5.1. Calculate the thermal conductivity of nitrogen gas, N2, at a temperature of 300 K and a pressure of 1 atm. The diameter of a nitrogen molecule is 3.7 A or Armstrong. Specific heat capacity at constant volume CV equals 20.8 J/mol K, Avogadro's number, 6.022 times 10 superscript 2 superscript 3 mol superscript 1. KB equals 1.38 times 10 superscript 2 superscript 3 J/K. Guide to solve problem 5.1. Here equation 25 or any other appropriate equation will be suitable. The values of average velocity and lambda will be calculated before being substituted into the equation. Remember to convert the diameter of the gas from Armstrong to meter and the molar mass of the gas molecule from atomic mass unit, AMU, to kilogram. Note that 1 AMU equals 1.66 x 10 to 27 kilograms. When all this are done well, you will be happy to obtain the thermal conductivity of the nitrogen gas as 0.026 W/m.K. 5.6. The diffusion coefficient of gases. The diffusion coefficient, D, is a measure of how quickly gas molecules spread out, diffuse, from areas of higher concentration to areas of lower concentration. In other words, it quantifies the rate at which molecules move through a gas due to random molecular motion. The diffusion coefficient is important for understanding how gases mix, transfer momentum, and move across barriers. Equation 26a shows an expression for its calculation from average velocity, u average, and mean free path length, lambda. While equation 26b shows it calculation from Boltzmann's constant, Kb, temperature, T, molecular diameter, d, and dynamic viscosity, eta. When all units of these physical parameters are in SI units, the unit for diffusion coefficient of gases will be in square meter per second. 5.6.1 Interpretation of the equation for the calculation of the diffusion coefficient of gases. Temperature dependence. As the temperature increases, the diffusion coefficient increases because molecules move faster and spread out more quickly. Viscosity and molecular size. A gas with higher viscosity or larger molecules will have a lower diffusion coefficient because it encounters more resistance to movement. This is perfectly illustrated by the Graham's law of diffusion. The rate of diffusion of gases is inversely proportional to the square roots of their molar masses. 5.6.2 Practical applications of the diffusion coefficient of gases. 1. Gas mixing. Understanding diffusion is essential in industries where gases need to be mixed, such as in chemical reactors, breathing gases, and pollution dispersion. 2. Environmental science. Diffusion coefficients help predict how pollutants or gases like carbon dioxide spread through the atmosphere. 3. Engineering. In processes such as aeration, separation, or fuel cell operation, the diffusion coefficient is crucial for optimizing performance. 6.0 Real gases. Real gases are gases that do not behave exactly as ideal gases under all conditions. While ideal gases are a theoretical concept that follow the ideal gas law, PV equals nRT, perfectly, real gases exhibit deviations from this behavior due to interactions between gas molecules and the finite volume of the gas molecules themselves. The picture here shows the random movement of the ideal gas molecules without any form of attractive force within the molecules, unlike the case of the real gas molecule that have some forces of attraction within the molecules. These deviations become more pronounced under conditions of high pressure and low temperature. So, the ideal gas law works well at low pressures and high temperatures. Real gases deviate from ideal behavior at high pressures or low temperatures. 6.1 Key characteristics of real gases. 1. Intermolecular forces. Real gas molecules experience intermolecular forces, including attractive forces, e.g., van der Waals forces, which cause gas molecules to be drawn closer together. Repulsive forces, which become significant when molecules are very close to each other. These forces are absent in ideal gases, where molecules are assumed to have no attraction or repulsion. 2. Molecular volume. Ideal gas theory assumes that gas molecules have no volume. However, real gas molecules occupy a finite volume, and this becomes significant at high pressures when molecules are packed closer together. The volume of the molecules themselves is no longer negligible compared to the container's volume. 3. Deviation from ideal gas law. Real gases follow the ideal gas law more closely at high temperatures and low pressures. However, As pressure increases and temperature decreases, the deviation from ideal gas behavior becomes noticeable due to the intermolecular forces and finite molecular volume. 4. Behavior at high pressure and low temperature. High pressure. At high pressure, gas molecules are forced closer together, and intermolecular forces, both attractive and repulsive, start to have a noticeable effect, causing deviations from the ideal gas law. Low temperature. At low temperatures, gas molecules move more slowly, and attractive forces between molecules become significant, which may lead to condensation, gas turning into liquid, under certain conditions. 6.2. Differences between real gases and ideal gases. The table here summarizes the differences between the two gases using 6 properties, which include intermolecular forces, molecular volume, behavior at high pressure, behavior at low pressure, pressure-volume relationship, and volume at high pressure. Learners and viewers should go through these differences carefully, as these are the modification of the kinetic theory of gases to fit the real gases. Equation 15, as restated here, shows the relationship between the pressure and the average kinetic energy, K.E, of the ideal gas, while equation 27 shows the relationship between the pressure, P, and total kinetic energy of the real gas. Equation 15 shows that the pressure of ideal gases are independent of volume, while equation 27 shows that the pressure of real gases are inversely dependent on volume. These equations buttress the differences between ideal and real gases as stated in this study. 6.3 Real gas equations. 6.3.1 Van der Waals equation of state. The equation 28 shown here is the van der Waals equation of state. It is a more accurate equation than the ideal gas law for describing the behavior of real gases, especially at high pressures and low temperatures, where deviations from ideal gas behavior are most noticeable. The van der Waals equation modifies the ideal gas law to account for two main factors that ideal gases do not consider. 1. Intermolecular forces, attractive forces between gas molecules. 2. Finite molecular volume, the volume occupied by the gas molecules themselves. 6.3.1.1 Practical explanation of van der Waals equation of state. The ideal gas law assumes that gas molecules do not interact with each other, no attraction or repulsion, and that their volume is negligible. This is true for many gases at high temperatures and low pressures, where the molecules are far apart. However, real gases deviate from this idealized behavior, especially at 1. High pressures. Molecules are compressed and experience significant intermolecular forces, leading to attractive forces between molecules. 2. Low temperatures. Molecules move more slowly, which makes the effect of intermolecular attractions more noticeable. The van der Waals equation accounts for these factors. 1. Molecular size. It corrects for the fact that molecules have a finite size and occupy space. At high pressures, this becomes important because the gas molecules are packed closely together, reducing the free space for their movement. 2. Intermolecular attractions. It adjusts for the fact that gas molecules experience attractive forces, which lower the pressure of the gas because these forces pull the molecules closer together. Equation 28 shows the van der Waals equation, with the parameters described below. P equals pressure of the gas. V equals volume of the gas. T equals temperature of the gas. N equals number of moles of gas. R equals ideal gas constant. A equals constant that accounts for the attractive forces between molecules. B equals constant that accounts for the finite volume occupied by gas molecules. 6.3.1.2 Explanation of each term in the van der Waals equation. 1. A/V square. The term A represents the intermolecular attractive forces, such as van der Waals forces, that exist between molecules. At high pressures or low temperatures, these attractive forces become significant because the molecules are closer together, leading to a decrease in the observed pressure compared to that predicted by the ideal gas law. The A/V square term increases the pressure of the real gas to account for these attractive forces. This term becomes significant at high densities. 2. V minus B. The term B accounts for the finite size of gas molecules. In the ideal gas law, the volume of the gas molecules is assumed to be zero, but in real gases, molecules occupy a certain volume. At high pressures, when the gas molecules are compressed, the volume occupied by the molecules themselves becomes important, and this term corrects the volume. B represents the volume occupied by the molecules themselves and reduces the available volume for gas molecules to move, making the real gas behave differently from the ideal gas. 3. Equation's purpose. The van der Waals equation attempts to make up for the limitations of the ideal gas law, especially when gases are not behaving ideally. It is particularly useful in understanding the behavior of gases under extreme conditions, e.g., high pressure or low temperature, where the ideal gas law fails. The equation explains gas condensation, transition from gas to liquid, and helps predict the critical temperature and critical pressure of gases, where the distinction between gas and liquid phases disappears. 6.3.1.3 Real-world applications. 1. Liquefaction of gases. The van der Waals equation can predict the conditions under which gases like oxygen, nitrogen, and carbon dioxide will liquefy, when they are cooled or compressed to a point where their attractive forces dominate. 2. Critical point. It helps to define the critical temperature and critical pressure of a gas, which are essential in understanding the phase transition between gas and liquid. 3. Engineering and industrial applications. The van der Waals equation is useful in gas storage, cryogenics, and other industrial processes that deal with gases under extreme conditions, high pressure, low temperature. Solved problem 6.0. Calculate the pressure of 1 mole of carbon dioxide, CO2, at a temperature of 300 K and a volume of 0.5 liters using the van der Waals equation. The van der Waals constants for CO2 are A equals 0.364 J m superscript 3 / mole superscript 2 and B equals 4.27 times 10 m superscript 3 / mole. Gas constant R equals 8.314 J / mole K. Solved problem 6.0 is done using equation 28. Here the pressure, P, is made the subject of formula and the given parameters substituted, ensuring that all parameters are in the agreeable units or SI units. Learners and viewers should attempt to make other physical quantities the subject of formula in case there is a need to solve for those quantities rather than the pressure. 6.3.2 Virial equation of state. The equation 29 is the virial equation of state. It is also a more generalized equation than the ideal gas law, and it describes the behavior of real gases more accurately, especially at high pressures and low temperatures where the ideal gas law fails. The equation is based on the virial equation, which is derived from the intermolecular forces between gas molecules and the finite size of the molecules themselves. 6.3.2.1 The key components of the virial equation. 1. Ideal gas behavior. The term 1/Vm corresponds to the ideal gas behavior, which is simply the inverse of molar volume. In ideal gases, the equation reduces to the ideal gas law, PV equals nRT, where n is the number of moles. 2. Virial coefficients. The first virial coefficient B, T, accounts for the intermolecular forces, like attraction or repulsion, and the finite volume of the gas molecules. At low temperatures and high pressures, attractive forces between molecules become significant, and B, T, becomes negative, indicating that the gas is more likely to condense. At high temperatures and low pressures, B, T, is positive, reflecting the repulsive interactions as molecules begin to push away from each other. The second virial coefficient C, T, can account for more complex interactions, such as three-body collisions, though it is often neglected for many practical applications. 3. More terms. Higher-order terms, e.g., Ct/V cubic m, become important at extremely high pressures but are rarely used in common applications unless the gas is subjected to very high pressures. Where P equals pressure of the gas, T equals temperature of the gas, R equals gas constant, Vm equals molar volume, volume per mole of gas, B, T, C, T, etc. equals temperature-dependent virial coefficients. 6.3.2.2 Practical uses of the virial equation. 1. Predicting gas behavior. The virial equation helps predict the behavior of gases when they are not behaving ideally. For instance, at high pressures or low temperatures, real gases exhibit behavior such as condensation, which cannot be described by the ideal gas law. The virial equation allows for more accurate modeling of gases under these conditions. 2. Intermolecular interactions. The virial coefficients provide valuable information about the nature of intermolecular interactions. Attractive forces, via B, T, can help predict when gases will condense into liquids. Repulsive forces can explain the volume behavior of gases at high pressures. 3. Equation of state for non-ideal gases. The virial equation is often used in situations where gas is subjected to conditions outside the range of ideal gas law applicability, such as in supercritical fluids or high-density gases. 4. High-pressure gas dynamics. The virial equation is used in engineering fields, particularly for designing processes involving gases at high pressures, like in gas pipelines, storage tanks, and chemical reactors. Problem 6.0. Calculate the pressure of 1 mole of a gas at a temperature of 300 K and a volume of 0.5 liters using the virial equation of state, truncated to the second term. The second virial coefficient, B, is minus 0.021 m superscript 3/mol. To guide the learners and viewers on how to solve problem 6.0, equation 29 is used. Substituting the given parameters into the virial equation, equation 29 directly and truncated to the second term will give a negative value for the pressure, which is not the correct answer. Rather, equation 29 should be converted into quadratic equation of the form P equals nRT/V plus n square RTB/V square. Here the pressure of the gas equals 2.894 times 10 Pa. 6.3.3, Soave-Redlich-Kwong, SRK, equation. Equation 30 is the Soave-Redlich-Kwong, SRK, equation of state. It is a modification of the original Redlich-Kwong equation. It is widely used to describe the behavior of real gases, particularly in the context of non-ideal gas behavior at high pressures and low temperatures. The SRK equation is particularly effective for modeling hydrocarbons, chemical process systems, and gas-liquid equilibrium. The SRK equation of state is an equation that models real gas behavior by accounting for intermolecular forces and the volume occupied by gas molecules. It is especially useful in the chemical engineering and petroleum industry for predicting phase behavior and compressibility factors in gases and liquids, where P equals pressure of the gas, R equals universal gas constant, T equals temperature, V equals molar volume of the gas, volume per mole. A equals a constant that reflects the intermolecular attractive forces between molecules, usually obtained from critical constants. B equals a constant that accounts for the finite size of gas molecules, also related to the critical volume. Alpha, T, equals a temperature-dependent function that adjusts the attractive force term. The introduction of this temperature-dependent factor allows the SRK equation to better represent real gas behavior, especially near the critical point. 6.3.3.1 The key features of the SRK equation. 1. Critical constants. The constants A and B are related to the critical constants of the gas, which describe the behavior of the gas at its critical point. These constants can be derived from experimental data or estimated for a wide range of gases. 2. Phase behavior and compressibility. The SRK equation is particularly useful for modeling the phase behavior of real gases, especially near the critical point, where deviations from ideal gas behavior are significant. It can also be used to compute the compressibility factor Z, which is a measure of how much a gas deviates from ideal behavior at different pressures and temperatures. 3. Applicability to hydrocarbons. The SRK equation is often used to describe hydrocarbons and other substances that show significant deviations from ideal gas behavior, particularly in the petroleum and chemical industries. 6.3.3.2 Practical application of the SRK equation. 1. Gas and liquid equilibrium. The SRK equation is often used to predict gas-liquid equilibrium and phase separation in chemical reactors, particularly in natural gas processing and petrochemical production. By modeling the non-ideal behavior of gases, engineers can predict when gas will condense into a liquid under different temperature and pressure conditions. 2. Predicting vapor-liquid equilibria, VLE. The SRK equation can be used to estimate vapor-liquid equilibrium, VLE, which is essential in designing distillation columns, separation processes, and other operations in the oil and gas industry. 3. Critical point and phase diagrams. The SRK equation helps in predicting the critical point of a gas and understanding how it behaves as it approaches the liquid-gas transition phase. The temperature dependence in the equation makes it ideal for modeling phase diagrams, including the supercritical fluid phase. 4. Non-ideal gas compression. The SRK equation can also be used to calculate the compressibility factor Z, which helps engineers understand how much a gas will compress or expand under given conditions. Solved problem 6.1. Calculate the pressure of 1 mole of propane, C3H8, at a temperature of 350 K and a volume of 0.1 liter using the SRK equation. The critical temperature, Tc, and critical pressure, Pc, of propane are 369.83 K and 42.48 bar, respectively. The acentric factor, omega, is 0.152. Solution to solve problem 6.1 includes 2 steps. Step 1. The parameters in equation 30 are calculated from the given quantities, as shown here. Step 2. The calculated parameters in step 1 are substituted into equation 30, as shown here. The pressure of propane is approximately 2.3 times 10 Pa or 23 bar. 7.0 Application of the concept of real gases. 7.1 Production of liquefied natural gas, LNG. The liquefied natural gas, LNG, is made of methane with the highest composition of about 80% with few amounts of ethane as well as minute concentrations of propane and butane. The LNG process is a practical example of how the concept of real gases is applied in real-world industrial processes. The process of liquefying natural gas involves transforming the gas from its natural state at ambient temperature and pressure into a liquid by applying pressure and lowering the temperature. This is based on the understanding of gas behavior and intermolecular forces in real gases, which deviate from ideal gas behavior, especially under extreme conditions. 7.1.1 The liquefaction process. Step 1. Compression. Natural gas, which is primarily composed of methane, CH4, is compressed to a high pressure, up to 1000 psi or 68 atm, in order to bring the gas molecules closer together. This step increases the density of the gas and reduces the volume of the gas. Real gas behavior in compression. As the gas is compressed, attractive intermolecular forces become more pronounced. The molecules move closer together, and the gas begins to exhibit a behavior different from the ideal gas law, which assumes that the molecules have no volume and do not interact. Step 2. Cooling, cryogenic cooling. The compressed gas is then cooled to a temperature that is below its boiling point at standard pressure, typically around -161 degrees Celsius, 112 K. At this temperature, methane turns into a liquid because its kinetic energy is reduced enough to allow the intermolecular forces to take over. Real gas behavior in cooling. As the temperature drops, the gas molecules lose kinetic energy, and attractive forces, such as van der Waals forces, dominate, causing the gas molecules to come together and form a liquid. The cooling step is designed to exploit the temperature-dependent nature of the intermolecular forces, which are incorporated into real gas equations like the van der Waals equation and virial equation. Step 3. Storage and transportation. The liquefied gas, now in liquid form, is stored at a very low temperature in cryogenic tanks and transported as LNG. During transportation, the liquid is maintained at a constant low temperature to prevent it from returning to its gaseous form. 7.2. Production of liquefied petroleum gas, LPG. Liquefied petroleum gas, LPG, is also known as cooking gas. Its production involves the processing of hydrocarbon mixtures, primarily propane and butane, which are derived from natural gas and crude oil refining. The production process relies on the principles of real gases, as these hydrocarbons exhibit non-ideal behavior under various temperature and pressure conditions. 7.2.1 Key processes. 7.2.1.1 Separation. LPG production begins with the separation of propane and butane from other hydrocarbons in natural gas or crude oil. This is achieved through various separation techniques, such as distillation or absorption, which take into account the different boiling points and properties of the hydrocarbons. 7.2.1.2 Compression and cooling. The separated propane and butane are then compressed and cooled to facilitate liquefaction. This process exploits the real gas behavior of these hydrocarbons, where increased pressure and decreased temperature cause them to deviate from ideal gas behavior and eventually liquefy. 7.2.1.3 Liquefaction. As the compressed and cooled gas mixture is further processed, the propane and butane are liquefied under pressure. The real gas behavior of these hydrocarbons is critical in this step, as their properties dictate the conditions required for liquefaction. 7.2.1.3 Purification. The liquefied gas is then purified to remove impurities and other hydrocarbons. This step ensures the production of high-quality LPG that meets specific standards for domestic and industrial use. 7.2.1.4 Storage and distribution. Finally, the LPG is stored in pressurized containers or cylinders and distributed to end users. The real gas behavior of LPG is crucial in designing and operating these storage and distribution systems, as the properties of the gas must be carefully managed to ensure safe and efficient handling. 7.2.2 The real gas principles in LPG production. The production of LPG relies on the principles of real gases in several ways. Non-ideal behavior. LPG components, such as propane and butane, exhibit non-ideal behavior under various temperature and pressure conditions. This behavior is accounted for in the design and operation of LPG production facilities. Compressibility. The compressibility of LPG components is critical in the compression and liquefaction steps, where the gas is compressed and cooled to facilitate liquefaction. Phase behavior. The phase behavior of LPG components, including their boiling points and vapor-liquid equilibria, is essential in designing separation and purification processes. By understanding and applying the principles of real gases, LPG producers can efficiently and safely produce high-quality fuel for various applications. 7.3 Production of compressed natural gas, CNG. CNG is natural gas with more than 80% methane in composition, which is stored at high pressure, typically around 200 to 250 bar, 3000 to 3600 psi. This compression reduces the volume of the gas, making it feasible to store and transport it more easily, especially for applications like vehicle fuel and gas supply. The CNG process primarily focuses on compressing natural gas to reduce its volume for efficient transportation and use. The gas remains in its gaseous phase, but at a much higher density than at standard conditions. 7.3.1 Real gas behavior in the CNG process. In the CNG process, the gas behaves as a real gas, meaning its intermolecular forces and molecular volume become significant, particularly under high-pressure conditions. Real gas behavior deviates from the ideal gas law, which assumes no intermolecular forces and no molecular volume. 7.3.2 Here's how real gas concepts apply to the CNG process. 7.3.2.1 Compression of natural gas. Boyle's law and real gas effects. The process of compressing natural gas is governed by Boyle's law for ideal gases, which states that at a constant temperature, pressure is inversely proportional to volume. However, real gases do not behave ideally at high pressures. As the gas is compressed, the molecules are brought closer together, and intermolecular forces, such as van der Waals forces, become significant. At high pressures, attractive intermolecular forces between gas molecules reduce the volume more than predicted by ideal gas behavior. The repulsive forces also become significant at extremely high pressures, as the volume of the gas molecules themselves takes up space. Real gas equations, like the van der Waals equation or the Redlich-Kwong equation, are used to accurately predict gas behavior in this stage. For example, the van der Waals equation modifies the ideal gas law to account for molecular size and intermolecular forces. As in equation 28 of this study. 7.3.2.2 Gas storage and transport. Once the gas is compressed, it is stored in high-pressure cylinders or tanks. The compressibility of natural gas, how much it can be compressed into a given volume, is critical in determining the efficiency of storage and transportation. Real gas behavior is especially important when considering the compressibility factor, Z, which quantifies how much the gas deviates from ideal gas behavior. For a real gas, the compressibility factor Z is Z equals 1 for an ideal gas. Z less than 1 for gases that are more compressible than ideal gases, typically at high pressure. Z greater than 1 for gases that are less compressible than ideal gases, typically at low pressure. By applying real gas equations and understanding the compressibility factor, engineers can optimize the storage and transportation of CNG, ensuring that the gas remains safe and efficient for use in vehicles or other applications. The compressed natural gas (CNG) process is an important example of how the principles of real gas behavior are applied in the storage and transportation of natural gas, primarily methane (CH4), in its compressed state. The process involves compressing natural gas to a high pressure to make it more efficient to store and transport, while accounting for real gas effects such as intermolecular interactions and volume restrictions that go beyond ideal gas behavior. 7.4 Separation of the component of air. The separation of air components, such as oxygen, nitrogen, and argon, is a complex process that relies on the principles of real gases. Air separation is typically achieved through cryogenic distillation, which involves cooling the air to extremely low temperatures and then separating the components based on their different boiling points. 7.4.1 Key processes in separation of the component of air. 1. Air compression and purification. The first step in air separation is to compress and purify the air to remove impurities such as dust, water vapor, and carbon dioxide. This is essential to prevent contamination and ensure efficient separation. 2. Cooling and liquefaction. The compressed air is then cooled to extremely low temperatures, typically around -180 degrees Celsius, using heat exchangers and refrigeration systems. At these temperatures, the air is liquefied, and the real gas behavior of the components becomes significant. 3. Distillation. The liquefied air is then separated into its components through cryogenic distillation. This process relies on the different boiling points of the components, such as oxygen, -183 degrees Celsius, nitrogen, -196 degrees Celsius, and argon, -186 degrees Celsius. The real gas behavior of these components is critical in this step, as their properties dictate the separation efficiency. 4. Separation of components. As the air is distilled, the components are separated based on their boiling points. Oxygen, nitrogen, and argon are collected separately, and their purity is ensured through additional purification steps. 5. Storage and distribution. The separated gases are then stored in tanks or cylinders and distributed to various industries, such as medical, aerospace, and manufacturing. 7.4.2 Real gas principles. The separation of air components relies on the principles of real gases in several ways. 1. Non-ideal behavior. The components of air, such as oxygen, nitrogen, and argon, exhibit non-ideal behavior at low temperatures and high pressures. This behavior is accounted for in the design and operation of air separation facilities. 2. Phase behavior. The phase behavior of the air components, including their boiling points and vapor-liquid equilibria, is essential in designing the cryogenic distillation process. 3. Thermodynamic properties. The thermodynamic properties of the air components, such as their specific heats, enthalpies, and entropies, are critical in designing and optimizing the air separation process. By understanding and applying the principles of real gases, air separation facilities can efficiently and safely produce high-purity gases for various industrial applications. 8.0 Joule-Thomson experiment. Joule-Thomson experiment, also called Joule-Kelvin experiment. The Joule-Thomson experiment investigates how the temperature of a real gas changes when it expands from high pressure to low pressure without exchanging heat with its surroundings, i.e., adiabatic expansion through a porous plug or valve. 8.1 Experimental setup. A gas is forced through a porous plug or narrow valve from a high-pressure chamber, P, to a low-pressure chamber, P2. Both chambers are thermally insulated, so the process is adiabatic, no heat exchange. Temperature is measured before and after expansion. 8.2 Key observation. For real gases, the temperature often drops during expansion. This temperature change is due to intermolecular forces, a behavior not seen in ideal gases. When a real gas expands, work is done by the gas to overcome intermolecular attractions. This work comes at the cost of internal energy, causing the temperature to drop. In some cases, like hydrogen or helium at room temperature, the temperature may increase due to dominance of repulsive forces. This is known as Joule-Thomson inversion behavior. 8.3 Joule-Thomson coefficient, μJt. The Joule-Thomson coefficient, μJt, is as shown in equation 31. It describes how temperature changes with pressure at constant enthalpy. If μJt is 0 or positive, the gas cools upon expansion. If μJt is 0 or negative, the gas warms upon expansion. 8.4 Application of the Joule-Thomson experiment. A gas liquefaction, example, in air separation plants, LPG production. Refrigeration and cryogenics. Understanding the thermodynamic behavior of real gases. Solved problem 8.0. During a throttling process of a real gas, the temperature of the gas drops from 325 K to 315 K as the pressure drops from 6.0 MPa to 4.0 MPa. Calculate the Joule-Thomson coefficient, μJt, for this process. The solution to this problem is as shown here. It simply involves substituting the given values for temperatures and pressures into equation 31b, as this is a throttling, isenthalpic process. The result is a positive value of the Joule-Thomson coefficient, which shows that cooling took place and liquefaction of the real gas. Problem 8.0. A gas has the following properties at a given state. Volume per mole V equals 0.025 m3/mol. Temperature T equals 300 K. A specific heat at constant pressure, Cp equals 29 J/mol.K. The gas obeys the van der Waals equation with constants. A equals 1.36 Pa/m6.mol2. B equals 3.18 times 10⁻⁵ m3/mol. Calculate the Joule-Thomson coefficient, μJt, at this state. To guide learners and viewers to solve problem 8.0, equation 31c will be appropriate, as it is modified to the expression 1 divided by specific heat capacity into 2A divided by RT minus B. This gives 3.65 K/bar as the answer, showing that cooling took place and the gas was liquefied. Here are some notable companies in the world that provide services related to gases, including production, distribution, and equipment. In Europe, we have 1. Linde Group. Services: industrial gas production and supply, oxygen, nitrogen, hydrogen, etc., gas equipment, medical gases, and cryogenics. Website: https://www.linde.com. 2. Air Liquide. Services: provides industrial gases for various applications, including healthcare, electronics, energy, and manufacturing sectors. Website: https://www.airliquide.com. 3. Praxair, now part of Linde. Services: industrial gases, gas distribution, and related services across multiple industries including healthcare, chemicals, and energy. Website: https://www.linde.com. 4. Air Products. Services: provides atmospheric, process, and specialty gases along with equipment and services, focusing on industries like energy, chemicals, and food production. Website: https://www.airproducts.com. 5. Messer Group. Services: supplies industrial gases and gas-related technologies for sectors such as metals, food processing, chemicals, and electronics. Website: https://www.messer.com. 6. Gaz de France, Engie. Services: gas distribution and energy services, including natural gas supply and services related to gas storage, transportation, and infrastructure. Website: https://www.engie.com. 7. TE Technologies. Services: specializes in fusion energy and has applications for gas handling, energy production, and cutting-edge technology development. Website: https://www.tefusion.com. 8. BASF. Services: known for its chemical manufacturing, BASF also offers gases for industrial applications, particularly in the chemical and automotive industries. Website: https://www.basf.com. 9. TechnipFMC. Services: provides engineering services in the natural gas and oil sectors, including LNG, liquefied natural gas, solutions and gas production systems. Website: https://www.technipfmc.com. 10. SABIC. Services: a global leader in chemicals, including the production of gases used in various industrial applications, particularly in petrochemicals. Website: https://www.sabic.com. In America, we have 1. Air Products and Chemicals Incorporated. Services, supplier of industrial gases, oxygen, nitrogen, hydrogen, etc., gas equipment, medical gases, and cryogenic technology. They also offer gas distribution systems for various industries, including energy, healthcare, and manufacturing. Website https://www.airproducts.com. 2. Linde plc. Services, provides industrial gases for use in a variety of applications, such as healthcare, energy, food production, and electronics. Linde also supplies gas-related equipment and technologies. Website https://www.lindeus.com. 3. Praxair, now part of Linde. Services, industrial gases, gas distribution, and technology for applications across the healthcare, energy, chemical, and food industries. Praxair was acquired by Linde, but its services still play a major role in the U.S. market. Website https://www.lindeus.com. 4. Airgas, a subsidiary of Air Liquide. Services, supplies industrial gases, welding products, and related equipment for various industries, including manufacturing, healthcare, and construction. They offer both compressed and liquefied gases. Website https://www.airgas.com. 5. Matheson Trigas, Inc. Services, provides a range of gases for industrial, medical, and specialty applications, along with cryogenic and bulk gas distribution services. Website https://www.mathesongas.com. 6. Air Liquide USA. Services, offers a broad spectrum of gases for industries such as healthcare, energy, chemicals, food, and electronics, along with related technologies and services. Website https://www.airliquide.com. 7. The Williams Companies Incorporated. Services, specializes in natural gas infrastructure, including transportation, processing, and distribution. They also offer related services for the production of liquefied natural gas, LNG. Website https://www.williams.com. 8. Westair Gases and Equipment Incorporated. Services, supplies industrial, medical, and specialty gases along with the equipment necessary for their distribution, including regulators, cylinders, and other gas delivery systems. Website https://www.westairgases.com. 9. Chart Industries Incorporated. Services, provides cryogenic equipment and services, including solutions for LNG, hydrogen, and other industrial gas storage and transportation needs. Website https://www.chartindustries.com. 10. U.S. Nitrogen LLC. Services, specializes in nitrogen production and distribution, serving industries such as chemicals, energy, and environmental applications. Website https://www.usnitrogen.com. In Asia, we have 1. Linda India Limited. Services, provides industrial gases, oxygen, nitrogen, hydrogen, etc., gas equipment, and related services. They are involved in the supply of gases for industries such as health care, steel, food, and electronics. Website https://www.linda.in. 2. Air Liquide Asia Pacific. Services, industrial gases supply, including oxygen, nitrogen, hydrogen, and medical gases. They also offer solutions for energy, food, and healthcare industries in the Asia-Pacific region. Website https://www.airliquide.com. 3. Praxair India, now part of Linda. Services, supplies industrial gases and related technologies, with a strong focus on industries such as metals, chemicals, healthcare, and electronics. Website https://www.linda.in. 4. Teo Nippon Sanso Corporation. Services, offers a wide range of industrial gases, including oxygen, nitrogen, hydrogen, and specialty gases. They also provide gas equipment, solutions for energy production, and healthcare applications. Website https://www.tn-sanso.co.jp. 5. BASF South Asia. Services, BASF supplies gases and chemicals to various industries such as agriculture, automotive, electronics, and energy. They are also involved in providing solutions for the production of gases used in industrial processes. Website https://www.basf.com. 6. Huangshe Dongbei Special Gases Company, Ltd. Services, a Chinese company that specializes in producing and distributing industrial gases, including oxygen, nitrogen, and hydrogen for various industrial applications. Website http://www.dongbeigas.com. 7. Shanghai Baosteel Gases Company, Ltd. Services, focuses on providing industrial gases for the steel and metallurgy industries, including gases like oxygen, nitrogen, argon, and hydrogen. Website http://www.baosteelgases.com. 8. The Hong Kong Oxygen and Acetylene Company Limited, HKOAC. Services, offers industrial and medical gases, along with related equipment. They supply gases for industries such as construction, manufacturing, and healthcare. Website https://www.hkoac.com.hk. 9. Gulf Cryo. Services, Gulf Cryo is a leading supplier of industrial gases and cryogenic equipment. They provide gases for industries such as healthcare, energy, chemicals, and food processing across the Middle East and parts of Asia. Website https://www.gulfcryo.com. 10. Air Products Asia. Services, provides industrial gases such as oxygen, nitrogen, and hydrogen to industries including energy, food, chemicals, and healthcare. They also offer equipment and technologies for gas distribution and storage. Website: https://www.airproducts.com. In Africa, we have 1. Linde Group, South Africa. Services: provides a wide range of industrial gases, including oxygen, nitrogen, hydrogen, and medical gases, as well as related equipment and services for industries like healthcare, energy, chemicals, and manufacturing. Website: https://www.linde.co.za. 2. Air Liquide South Africa. Services: offers industrial gases, including oxygen, nitrogen, hydrogen, and carbon dioxide, alongside related technologies and equipment. Air Liquide serves industries like healthcare, energy, chemicals, and food processing. Website: https://www.airliquide.com. 3. Gaysec Africa. Services: specializes in the supply of gases and gas-related equipment. Gaysec offers products like oxygen, nitrogen, argon, and acetylene, serving a wide range of industries in Africa. Website: https://www.gaysec.co.za. 4. Nitrochem. Services: provides gases, including nitrogen, oxygen, and hydrogen, with an emphasis on the distribution and supply of industrial and specialty gases. Nitrochem serves various industries, including chemicals, steel, and healthcare. Website: https://www.nitrochem.co.za. 5. African Oxygen Limited, AFROX. Services: one of the largest suppliers of industrial gases in southern Africa, AFROX provides oxygen, nitrogen, carbon dioxide, and other industrial gases, as well as equipment and solutions for welding, food preservation, and healthcare. Website: https://www.afrox.co.za. 6. ExxonMobil South Africa. Services: while primarily known for its energy and oil business, ExxonMobil also offers gases like liquefied petroleum gas, LPG, and natural gas in South Africa, serving residential, industrial, and commercial sectors. Website: https://corporate.exxonmobil.com. 7. Petrogas. Services: a leading supplier of liquefied petroleum gas, LPG, and industrial gases in West Africa, with operations in Ghana, Nigeria, and several other countries. They serve residential, industrial, and commercial customers. Website: https://www.petrogas.com. 8. Total Nigeria Gas. Services: Total Nigeria offers natural gas services, including the production and distribution of compressed natural gas, CNG, and LPG across Nigeria and other West African regions. Website: https://www.total.com. 9. Oxygen and gases, Oxygen Africa. Services, a provider of industrial gases, including oxygen, nitrogen, and argon. Oxygen Africa serves industries such as steel manufacturing, chemicals, food production, and medical gases across Africa. Website http://www.oxygenafrica.com. 10. Gulf Cryo, Africa Operations. Services, Gulf Cryo provides industrial and medical gases, as well as cryogenic equipment and solutions. They serve sectors such as energy, healthcare, and manufacturing in North Africa and other parts of the continent. Website https://www.gulfcryo.com. 11. Greenville, Nigeria. Services, Greenville, Nigeria specializes in the supply of industrial gases, including oxygen, nitrogen, and argon, along with related technologies for various industries. Website https://www.greenvillenigeria.com. 12. Nigeria Liquefied Natural Gas, NLNG. Services, NLNG is a major player in the liquefied natural gas industry, providing LNG for export and domestic consumption. They are involved in the processing, distribution, and marketing of natural gas. Website https://www.nlng.com. 13. NIPCO Gas. Services, NIPCO is a leading Nigerian gas company that focuses on the distribution and supply of liquefied petroleum gas, LPG, natural gas, and compressed natural gas, CNG, across Nigeria. Website https://www.enipco.com.ng.